All right, now let's take a look at some other really exotic shapes. The rhombus and the kite. So the rhombus is just a parallelogram where all the sides have the same length, so we know those. The kite's even more interesting. That's where you sort of have these adjacent sides having the exact same length, like this. So it looks really like a kite. Now, suppose that we just know, all we know are the lengths of the two diagonals in each case. So we know that this length, let's say, is D1, and this length is D2. And similarly here. Just knowing the lengths of the diagonals, is it possible to directly report the area of these things? Turns out the answer is yes. And here's the amazingly simple formula. You ready? Ta-da! It's just 1/2 the product of the lengths of the diagonals. So 1/2 D1 times D2. Why in the world should we believe that? Well, it's real easy. Let me show it to you. So here is a nice, clean rhombus. This side's the same as that side, and it's a parallelogram. Now, let's pretend that this length here is the D2 side, just like in the picture, D2, and this side here is D1. Now, here's the important thing I want you to notice. If this whole thing is D1, this cuts this right in half. It's a bisector. It's actually a perpendicular bisector. So this is half of D1, and that's half of D1. I'm going to write that in there. So I'm going to write in here that this is D1 divided by 2. Okay, I want you to remember that. And remember, this entire length is D2. Now, let me cut this right along its long diagonal. Of course, it doesn't change the area at all if I just move the pieces around, as long as the pieces don't overlap. So the area of the thing intact is the same as the area of the two pieces together. And now check this out. If I put one here and put one here, what shape do I produce? I produce a perfect parallelogram. But now it's a parallelogram where I know that the base length is D2 and the perpendicular height is D1 divided by 2. So we know what the area is. It's going to be base times height. So it's going to be D1 divided by 2 times D2, which is exactly 1/2 D1 times D2. So there's the formula. Nothing to it. It's literally as easy as that. And I'll let you actually think about a similar argument for the kite. It works the exact same way, modified. And so you can see that this really makes sense. This formula makes sense because if you cut a rhombus in half, you get a nice parallelogram where one of the sides now is one of the diagonals, and the other side is half. And the height is half. All right, let's apply it. See this thing in action. Look at that pretty shape. Look at that. Nice. All right, here we go. I want to find D2, so one of the diagonals. If I know that the other diagonal is 10 and the entire area is 55, well, what do I do? Well, I apply the formula we just derived, and what I say is 55, the area, equals 1/2 the product of the diagonals. One diagonal is 10, one diagonal is mysterious. So that means 55 equals, well, half of 10 is 5. Divide both sides by 5, and I see that D2 equals 11. And what are the units? The units here are meters, so this equals 11 meters. Cool. Not a problem once you get it. It's sort of fun. You can sort of apply these things a variety of different ways. Let's find the area of the rhombus given here, where we're given that D1 equals the expression 3x plus 2, and D2 is given by 4x minus 6. All right, so what is the area? Well, the area is going to be 1/2 the product of these two. So it's going to be 3x plus 2 times 4x minus 6. I actually noticed that I could factor out a 2 from here. And when I do that, that 2 in the numerator and that 2 in the denominator can simplify a little bit. And so I'm just left with this for the area. Area equals 3x plus 2 times 2x minus 3. Now that's the way I would keep the answer. If it were me, if it were I would keep it like that. But suppose that someone wanted you to actually FOIL that out. Well, you can do that too. 6x squared, and then I've got negative 9x, and I've got 4x. That's going to be minus 5x minus 6. And so you could write it that way too, although I much prefer the factored. Always in life, if you can keep things factored, that's awesome. Pretty cool. Let's try one last one. Let's consider the kite issue. So let's find the area of the kite. We know the formula. The formula is you just can take 1/2 the product of the diagonals. But look what we've got here. We don't have a lot of diagonals. In fact, really, if you look at it carefully, this doesn't look good at all. I know that this is 75, which, by the way, means this is 75. I know this is 35, and since it's a kite, I know this is 35. I'm told that this little teeny length right in here is 28. Wow. Well, but I do know that this actually forms a right angle. With kites, we know that these diagonals form a right angle. So I've got a little right triangle here. I know the hypotenuse is 35. I know one leg is 28. I could use the Pythagorean theorem to find this. Or if you really are as sneaky as I am, 35, I realize, is actually 7 times 5. Then I look at 28 and realize that's actually 7 times 4. So remember, the most famous right triangle is a 3, 4, 5 right triangle. And what I have here is something by 4 times 7 by 5 times 7. This must be 3 times 7. It's a 3 times 7 by 4 times 7 by 5 times 7 right triangle. So I took a 3, 4, 5 right triangle, blew it up, expanding each length 7 times. So this is actually 3 times 7, which is 21. So that was a sneaky way of doing that. If you didn't like that, you could actually use the Pythagorean theorem to find that. This squared plus 28 squared equals 35 squared. When you solve that, you're going to get 21. Well, that means that this is 21. So actually, one of my diagonals I see now is 42. So that's cool. How am I going to find this? Well, I know this is 28. All I've got to do here is find this. Well, look, I've got another right triangle. I know this is 21. I know the hypotenuse is 75. And so actually, I can use the Pythagorean theorem to figure out this length, because this length squared plus 21 squared equals 75 squared. When we solve that, I see this length is 72. And so what do I see? Well, now I've got all the information I need. I know the area equals 1/2 the product of the diagonals. So one diagonal is this, which is 42. The other diagonal is this whole thing, which is 72 plus 28, which is 100. So this equals, well, half of 42 is 21 times 100 equals 21 with a bunch of zeros. So 2,100, and my units are inches squared, and that represents the area. Wow. So you can see that with a little bit of thinking and also a little bit of algebra, you can see how important the algebra is. We can actually find areas of really exotic objects.